Hi guys, it's your science teacher here. In this screencast, I hope to aim to go through everything in C1, the atomic structure of an atom, hopefully in quite a fun and interesting way, and I hope you really enjoy the video. So, the atomic structure starts off in looking at what is inside of an atom. Here I've drawn a little atom, and you can see that the atom has a nucleus, a center part, filled up with two different subatomic particles. The first one to look at is the positive proton, which has a charge of +1 and a mass of 1 atomic mass unit, and it is located, as I said, in that nucleus. Also, you have neutral neutrons, okay? And it's quite easy to remember neutrons because their name is like their charge, neutral, and that also has 1 atomic mass unit and found in the nucleus. The one exception which isn't found in the nucleus orbits the nucleus in shells and is called an electron. And it has a negative charge, a -1 charge. Now you have to remember its mass, and its mass is extremely small. It's in fact 1/2000 atomic mass units, which is almost zero, and it's found in shells, like I said, or you can say orbitals, whichever you prefer. And the reason why it's so important is because when you find elements in the periodic table, you see they have two numbers that accompany the element. And knowing the property of the subatomic particles is vital to understanding how the atom looks like and what the number of protons, neutrons, and electrons are inside of the atom. So using the periodic table, we can deduce how many protons, neutrons, and electrons are inside each atom. For example, with potassium here, it has 19 as the atomic number and 39 as the relative atomic mass. Now, what the atomic number tells us is how many protons we have in our nucleus. Now, it's sometimes called the proton number as well. And if you go back to that table and we look at the charge on our protons, it's +1, okay? And because atoms have to be neutral, the amounts of pluses and negatives in our atoms must be equals how many electrons you have in that atom also. Now, the relative atomic mass is the number of neutrons added to the number of protons, because of the fact protons and neutrons are the only thing in your atoms that really have mass. I said the electrons is so small that you can assume it's almost zero. So the relative atomic mass is the number of protons added to the number of neutrons. So in this case, you can work out the number of neutrons by just doing the top number minus the bottom number. So the number of neutrons will equal 39 minus 19, which equals 20 neutrons. So looking at this atom of potassium, we can safely say that it has 19 protons and electrons and 20 neutrons. It's also important to remember how we got to that modern model of the atom that we know today, that we've drawn all the way over on this side of our screen. So it started off when John Dalton suggested that all things were made up of atoms. And he just represented atoms with a simple sphere. Now, the reason why he used a model to represent an atom is because they're so incredibly tiny that you can't view them with microscopes. So he just drew a simple sphere to represent his atom. It got a bit more advanced though, however, when J.J. Thomson discovered that our atoms contained subatomic particles. He discovered the electron, and he discovered that electron from finding out that different atoms reacted in certain ways. So he proposed that there must be electrons in our atoms, and each atom must have a different amount of electrons. and he said that the electrons were surrounded by a sphere of positive charge. Now, we know that that's not the final model of our atom, however, it was a massive improvement on the previous one. And it got improved even further when Ernest Rutherford found out that the nucleus was positive, and also that most of the atom was empty space. Now, he found this out using the gold foil experiment. And the gold foil experiment, basically what he did was he fired alpha particles at really high speeds through gold foil. And he made 3 observations and 3 conclusions from this experiment. He observed that most of the alpha went straight through. Now you can see I just used that symbol for alpha. That also means alpha. So most of the alpha went straight through, and from this he concluded that most of the atom must be empty space. Now, if the plum pudding was to be correct, then all of the alpha particles would have followed this trend. Okay, all of them would have passed through. However, he noticed that a really small percent, so a small percent, came straight back. Now, from this, he realized that there must be a nucleus. Okay, there must be something central to that atom that it was bouncing off, and that the nucleus must contain nearly all of the mass of the atom. Now, he made one more observation, and that was that some of the alpha particles were deflected. And after doing radioactivity in physics, you'll know that alpha particles are positively charged. And the reason why they were deflecting, and he concluded, was that this nucleus had a positive charge, and 2 like things repel. Now, the model was taken even further by a man called Niels Bohr, and Niels Bohr came up with the electron configurations of atoms. He found out that the electrons fit into orbitals following a 2-8-8 rule. And that basically means that electrons can fill these electron orbitals, but there can only be a maximum of 2 electrons in the first shell, there can be 8 in the second shell, and there can be 8 also in the third shell. That's not necessarily meaning that there has to be that many in each shell, but there just can be. Now, the final person to discover something about the atom and taking it to the model that we use in GCSE is James Chadwick. And James Chadwick discovered the neutron. And you can kind of get why the neutron was the last to be discovered. The reason for that is because obviously it's neutrally charged, okay? It doesn't do cool things like swerving alpha particles. It can't do that. It can't react like the electrons. So the neutrons were the hardest to discover. Now, it's really important to know the structure of atoms when we're talking about elements, compounds, and mixtures. Elements can be found in the periodic table, which has been shown here, okay? That thing's called the periodic table. Perhaps the sexiest table in the world according to scientists. The periodic table shows all the different elements in. The elements are just basically one type of atom. For example, if you find hydrogen in the periodic table, hydrogen is made out of only hydrogen atoms. And what happens with atoms is sometimes they bond with other things, okay? For example, when carbon bonds with oxygen, you can make carbon monoxide or carbon dioxide, which you've probably heard of. And these are called compounds. And that was what happens when more than one type of atom chemically bonds. And sometimes you get these things called mixtures as well, when you have more than one element or compound that are not chemically bonded together as well. And I've just drawn some images of elements, compounds, and mixtures down here. So here's an element. I can tell it's an element because there's only one type of atom involved. Okay, they're blue. It's a diatomic atom, meaning that there's two of them. It's a molecule as well because it's bonded as well. You can see there's a bond going on between them two different atoms. So it's a molecule of an element. It could be something like hydrogen, chlorine, fluorine, for example. Down here I have a compound which shows two different types of atom that are chemically bonded together. You have a green atom here and a purple atom. This could actually be carbon dioxide or water because there's two different elements bonding together. And so this could be the carbon, these are the two oxygens, or this could be the hydrogen and these are the two oxygens for water. So this is a compound. Now, it's not a mixture because of the fact these two things aren't different. However, if we go down to the bottom and look at the bottom example showing a mixture, you can see that it has a compound over here. It has over here it has an element, and it has a different element over here, and they're all not bonded together. Now, mixtures are really common, okay, in nature because we don't often have closed systems with just one thing in, okay? So the air, for example, is a mixture, or the sea. And basically everything we use in modern day is mixtures because of impurities. Like I said, with mixtures, you can separate them. That's what makes them different from elements and compounds. And we're just going to look at a few techniques here that you can use in order to separate mixtures. One of them is distillation. And distillation works on the principle of heating, evaporating, condensing, and collecting. And using this setup, I'm going to show you that. So here you have a heater, okay, and this heater heats up this round bottom flask, and the mixture, one of the components will evaporate. Now, say if this was ink and water, water has a lower boiling point, and distillation separates on boiling points. Water has a lower boiling point, so it will condense up here. Will evaporate, I mean up here. Then it will go into what is called a condensing tube or a condenser. This one's a Leipzig condenser, and it will condense in here and then be collected in this beaker here. Notice there's also some cold water in here. The reason for that is to speed up the condensation process. Also, some other key things to notice about this distillation apparatus is water goes in at the bottom and it comes out at the top here. The reason for that is so the water stays cold throughout the whole time in the condenser. The next technique to separate mixtures is a technique called crystallization, and that's only used to separate soluble solids. What I mean by soluble solids is solids that have been dissolved in a liquid. For example, salt in water you could separate using crystallization. And all you do is you evaporate off the liquid and it will leave you with the solid. And the last technique I want to talk about is chromatography, and that separates using solubility. Now, as you can see, I've got three different mixtures here. I've got A, mixture B, mixture C. And you can see that they're definitely all mixtures because they at least have two components in each of them. And what you can also notice is that A and C have two of the same components here. And A and B have two of the same components there. Now, the reason why chromatography separates out mixtures, I said, was to do with solubility. What I meant by that was the chromatography paper is put into a liquid, which is usually water, and the water will rise up the chromatography paper and take the different components in the mixture with it. Now, things that are more soluble will travel further up the chromatography paper, and things that are less soluble will stay at the bottom because they're more attracted to the stationary phase, which is the paper. The mobile phase is the thing that's moving, which in this instance is water. Now, I'm just going to take the drawing of the atoms a little bit further and go into drawing electron configurations of atoms. Now, we said that Niels Bohr came up with a rule for drawing electron configurations, and that was the 2-8-8 rule, okay? And let's apply that to three different atoms here. We've got sodium, chlorine, and boron, and we have the information from the periodic table that's provided. And it says that sodium has 11 electrons here. And how do I draw that in? Well, first I will put the name of the element inside my atom, and I can draw 2 electrons in the first shell. Now, I always go north, east, south, west when drawing these. That might be a good little tip for the exams, drawing north, east, south, west. Now, I've only drawn 10 electrons so far. You can count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is 11 in sodium, so I'm missing 1. And that is the electron configuration of sodium. Chlorine, I'll do in a different colour, and it will look like this. I've got 17 electrons in chlorine, so that will fill up the first 2 shells very quickly. That's 10 electrons. Now I've only got 7 to go, so I'll go north, east, south, west, north, east, south, and now I've drawn 17, and it looks a lot better like this. I always do that north, east, south, west because it makes my drawings look a lot clearer for the examiner. And the last one is boron, which only has 5 electrons, so that will look just like that. Now, atoms can become ions when they lose or gain electrons. And because of this, they can become charged. They can either have a positive charge or negative charge, depending on whether they lose or gain electrons. The reason for the charge is because they have a proton and electron imbalance. There is either more protons than electrons or less electrons than protons, and we'll talk about that in a second when I draw a positive ion and a negative ion. So down here you can see that I have 2 ions. I have one of sodium and one of chlorine. When bonded, it makes sodium chloride. That's why I chose it, because they're really nice. Here I've drawn out what it says in the periodic table as well to help me draw it. So we'll just draw the 2 atoms up here. Now, Na has a positive charge. You can see here it's represented with this plus sign. And what this means is that your atom has lost electrons. I like to think of the charge like naughty children in my class. So if I lose electrons, I'm positive, I'm happy, and I will have a positive charge. And if I gain naughty children into my classroom, if I gain electrons, I'm negative, I'm not very happy. So what does that look like in terms of our orbital diagrams? Well, let's have a look. So with sodium, I'll draw that, and I've got my diagram of sodium above. However, this time I've lost 1 electron. So this will look like this, okay? And I no longer will have this outer shell drawn, okay? There's no longer an outer shell present. And you can actually get rid of the outer shell if you like, because it's not necessary. You'll also notice when drawing ions, if you don't finish with a full outer shell, then you've probably made a mistake. With chlorine has a negative charge, meaning it's gained an electron. The number next to it will tell you how many it's lost or gained. So chlorine has only gained 1, as there's no number next to it, so it's only got a -1 charge. So chlorine will have gained 1 electron. So what that will look like is just this. So exactly the same as above. However, this time it will have 1 more electron in its outer shell, and it now has a full outer shell. In fact, what I've drawn is sodium chloride. If they're next to each other and bonded, that is sodium chloride. Now, other things about atoms is you can have isotopes of different atoms. Now, what that actually means is that this relative atomic mass has changed of your atom. So these are 3 isotopes of carbon. Okay, you have carbon 12, 13, and 14. Now, if we go back to the very beginning of working out how to calculate the number of protons, neutrons, and electrons, we can quickly do that for these atoms of carbon. So this has 6 protons. It has 6 electrons and it has 6 neutrons. This one has 6 protons. It also has 6 electrons, but now it has 7 neutrons, and this one has 6 protons, 6 electrons, but now has 8 neutrons. So you can see what's happening is an isotope has the same number of protons and electrons, but a different number, but not the same amount of neutrons. And that's why you can end up with numbers like on Cl35 over here, okay? That's because there's 2 isotopes of chlorine. You have chlorine 35 and you have chlorine 37. Now you can see that there must be a lot more of chlorine 35 in the atmosphere because of the fact the relative atomic mass is 35.5. In fact, they're in a 3 to 4. They're in a 1 to 4 ratio. Okay, there's only 1 chlorine 37 for every 4 chlorine 35s. The last thing in this topic is looking at what happens when you have 2 compounds reacting and representing that using an equation. Now, the first thing about this equation I want to talk about is something called state symbols, and that's basically how you can represent each one of these compounds. Now, there's 4 key state symbols you need to know. The common states are obviously S for solid, you have G for gas, you have L for liquid, and you have AQ for aqueous. Now, adding state symbols to a reaction like this, it would usually tell you whether or not it's been dissolved in water or not, because that's what aqueous means. Aqueous just means dissolved in something. So sulfuric acid is usually found in an aqueous form. It would tell you in a question if it wasn't. This is aqueous, liquid for water, and K2SO4, that is also aqueous. So they're state symbols, and sometimes you get asked to add them to a reaction. Often it will tell you what form you found it in, or it will be a precipitate reaction and it would expect you to know that you've made a solid. Now, how to balance a reaction like this? What I always do is I draw a line down the center of my arrow, and I count up the number of atoms I have on each side. So on this side I have hydrogen, I have sulfur, I have oxygen, and I have potassium, and on this side I will also have hydrogen, sulfur, oxygen, and potassium. Now I count up how much of each of them I have on both sides. So on this side I have 3 hydrogens, I have 1 sulfur, I have 5 oxygens, I have 1 potassium, and on this side I have 2 hydrogens, I have 1 sulfur, I have 5 oxygens, and I have 2 potassiums. Now, am I happy currently? No, I'm not, okay? I'm not happy because they're not balanced, okay? And all reactions must be balanced. So I need to find a way of balancing this reaction. And I can't change numbers after an element because that would change the compound. I can only change the number at the start of an element. So I'll try and do that now. Now, what I always do is I always balance the metal first, or things that aren't oxygen and hydrogen, basically. I always balance them first. So let's do that. So there's 2 potassiums on this side, so I want 2 potassiums on this side. Now that changes my number of oxygens and hydrogens. And I'll show you how. So now there's 2 potassiums on this side, so I'm happy. But now there is an extra oxygen. So now 6 oxygens on this side, and there is now on this side 4 hydrogens. So I'm not happy. Now I'll go to the next thing. So I said that I'd leave hydrogen and oxygen to last. So sulfur, I'm happy because the fact they're balanced. But oxygen and hydrogen now aren't balanced, so I need to sort that out. There's 6 oxygen on this side and only 5 on this side, so I can increase that by adding another oxygen, by having another H2O. Now I've got 4 H is on this side, and I have 6 oxygens. And now you can see that you have a lovely balanced equation done and dusted. Thank you for watching this screencast.